Okay, so to find the electric field strength at a distance d from one end of the rod that has a charge q, we're going to break that charge on the rod up into like infinitely little small charges, dq. So I'm going to take a little tiny piece of charge right here. A little tiny charge right there. And that's going to be dq. And I know that if I had a little point charge over there, the electric field strength due to that point charge would be to the right. And that's just a little tiny piece of the electric field strength due to the whole rod. The electric field strength through the whole rod is just good old capital E. But the electric field strength due to just that little piece of charge, dq, well, that's a little piece of the E, dE. And as a direct result of what we did back here with a point charge, we know the formula to calculate, the electric field strength due to a point charge like that. So we use this fact now, ba-bam, ba-bam, and we basically say that dE would equal, what would it equal? Using that fact, we know. Okay, but we're going to say it the new sophisticated way. 1 over 4 pi epsilon 0 times dq well, this is d here and that's L. We're going to have to define another variable. Why don't we call it, I'm going to call it x. So it would be over x squared, like that, yes? But what's x from? Here. So that's x. X is the distance from dq to the point in question. So this here is our starting point. Which is really just a fancy-dancy way of saying this thing right here. I want you guys to get comfortable with doing the 1 over 4 pi epsilon 0. You'll see it a lot. It's very commonly written that way. So I just want you to get comfortable with it. 6 and 1 half dozen other. Okay. Exactly. So that's the electric field strength just due to that little dq right there. But of course, we're interested in calculating the whole electric field strength. So the whole electric field strength is the sum or the integral of all the dE's. If you take the sum of all the little tiny pieces of E, you get the whole E. E is the integral of all the dE's. Yes? So we can just keep writing this. This is going to be then the integral of 1 over 4 pi epsilon 0 times dq all over x squared. But now we're going to be integrating over q, because we're doing it for all the Q's. So what is our boundaries going to be there? If we're doing it for all the little DQs, we want to go from no charge to all of the charge, capital Q. Well, you can't use negative L to L type business until we change the DQ. And that's where we're going. But if you're saying the integral in terms of DQ, then you got to put the boundary conditions in terms of Q. Well, ultimately, we're going to rewrite DQ and change the location. But for now, we're just saying, look, we have to do this for all the charges, 0 to Q. So if this here is in terms of DQ, then the boundary conditions are going to be in terms of 0 to Q. In a moment, guess what we're going to change it to? Yeah, and DL is along the x-axis, so guess what it's going to be? A dx. Q is the charge of the whole rod right here. That's the total charge of the rod. So we have to integrate all of the charge. Yes, yes, yes. And that's why we're going to make a substitution right away, and we're going to change it into a distance type thing. But for now, we're just saying, hey, look, if we're going to integrate this for all the little pieces of Q, we have to do that for all of the Q, people. Yes, we're going to a distance location thing. That's next, right after the break. But this is where we start. Okay, so take a break, come on back. So we're going to replace DQ most times. So let's just kind of review the different ways we can replace DQ. So I'm going to put this problem on hold, little timeout here. And we could say that, remember how like density equals mass divided by volume? Yes? Well, that's called the mass density. Exactly. And if you want it to be really technical, you could put a little subscript here and say rho sub m. Yes? Well, the charge density is rho sub q. And it's not the whole mass divided by the whole volume, but guess what it is? The whole charge divided by the whole volume. Yeah, it is. It is. But in this case, it's the charge of the object divided by the volume, and that's charge divided by the voltage across the plates. Okay. Exactly. So I'm just showing the different cases, and that's exactly what we're going to use, Tyler. So that's one option, and if we use that, basically, we could say that charge would equal the charge density times the volume. Yes? I'm going to stop drawing the Q, because everything we're going to be doing right now is in terms of charge. So if the whole charge is equal to the whole charge density times the volume, well then a little piece of charge would equal the charge density times a little piece of the volume. So this is one substitution we could make for dq. That's not the one we're going to use in this case, but in general, that's one we could use. Then we also have the surface area charge density. And that's sigma and sigma is the amount of charge per area. The units would be coulombs per meter squared. And of course, if we rearrange that, the whole charge would equal the surface area charge density, sigma, times the area of the surface. Therefore, a little tiny piece of the charge, dq, that would equal the surface area charge density times dA, a little tiny piece of the area. So that's another substitution. In some of the cases, you're going to have to make that substitution for dq. And you're going to integrate over the area, dA. And last but not least, you have the linear charge density. And the linear charge density, does anyone remember? And again, you could put a little q here if you wanted to, because there's also yeah. But the symbol for the linear charge density is lambda. Very good memory. And of course, guess what it's going to be equal to? The charge per length, units coulombs per meter. So if you rearrange this, then we get the whole charge would equal the linear charge density times the whole length. Therefore, a little tiny piece of the charge, dq, would equal the linear charge density times a little tiny piece of the length. But usually, that little tiny piece of the length is called like dx or dy or dr. You could call it dl, but it's just commonly to call it some other little piece of length. So, you know, dl sometimes is called dx, or sometimes it's called dy, or sometimes it's called dr, or sometimes it's called dz. Depends on how you set up your diagram. It's really 6 in one, half a dozen in the other, you know, what you want to integrate it over. And in this problem that we're currently working on, since we want to do it over the whole length, we could call it dl. We could call it dl. But I already established that, look, from dq to the point in question right here, that distance is x. And we already have an x in our formula right here. So to make it look like it all jives here, we want to integrate over x. So basically, I want to change this dq into a dx. So I'm going to use that third one right here, and I'm going to say, well, dq is equal to the linear charge density times dx. So now I say here the electric field strength is going to equal the integral of 1 over 4 pi epsilon 0 times dq, but guess what I'm going to write in instead of the dq? Lambda dx all over x squared. That's a good question. I just want to make sure. Now, due to symmetry, I could integrate this from here to there and get all of the dx's, or I could integrate it from here to there. You know, I could have drawn my diagram differently. So it doesn't really matter whether I integrate from here to there or from there to there. And I'm going to choose to integrate it with the dx's going out this way here. So my first value of x, because look, I'm integrating an x variable right here. My first value of x is going to be right here. Well, how far away am I from the point of interest right here? At this point here, and here's my point of interest. How far away am I at that first point of, when I'm doing my dq right here at that end? D. So my first boundary condition is going to be from D, and then I'm going to do it all the way over here, and at that point there, what's the value of x, the distance between the two? D plus L. And now it's just a pure calculus problem. So we just plunge ahead. We could do that at the end. You could do it now, or you could do it at the end. Most people do it at the end. Not really. So when you integrate x to the negative 2, what does that come out to? Negative 1 over x. And then the boundary conditions are d to d plus L. So that's going to be 1 over 4 pi epsilon 0 times lambda parentheses negative 1 over d plus L minus negative 1 over common denominator. That ultimately ends up being E equals 1/4 pi epsilon 0 times lambda times L over D plus L times D. That's after you get a common denominator. But last but not least, what do we know lambda equals? Q over L. So we have E equals 1/4 pi epsilon 0 times Q over L times L over D plus L D. The L's cancel out. And then last but not least, let me make room right over here. E equals 1/4 pi epsilon 0 times Q all over D plus L times D. Woohoo! Chicken